Hi everybody, hopefully I can be heard okay. My name is Alistair Miles. I'm based at the University of Oxford, also work at the Wellcome Sanger Institute in the UK. I'd like to tell you about some work that I've been involved in to develop new software for storing large multidimensional arrays called Zarr. So normally when I go to conferences, this is what I talk about. I'm part of a group that studies the mosquitoes which carry malaria in Africa. And we use genome sequencing to study how these mosquitoes are evolving, particularly how they're evolving resistance to the insecticides that are used to control them. And so the question is, what am I doing giving a talk about data storage? And the reason that I'm giving this talk is because our science has been scaling up over the last few years. So in the first 4 years of our work, we sequenced about 1,000 mosquitoes collected from the field in different African countries. Now we can sequence 10,000 mosquitoes every single year. So we have a data volume issue, and that means that we need new tools to address that. We've been using the SciPy stack since the beginning of the project, and that's been just fantastically empowering. It's been an amazing asset for our project, but with the large data volumes come new challenges. So I'm going to try and explain the basic motivation for doing this work and do it in a reasonably general way. So basically, we have problems that look like this. So we have some multidimensional array, which is our input data. And in our case, this is the length of this first dimension. That's the number of bases in the mosquito genomes. This is about 200 million. And then the second dimension here are the mosquitoes that we've studied, so we might have 10,000. And then in our case, actually, we only have 2. The depth of our third dimension is 2, because mosquitoes carry 2 copies of their genomes like we do, 1 from each of their parents. But this is a very general schema, and we want to do some sort of computation, and the output of our computation is going to be some other multi-dimensional array. And in general, actually, there may be multiple input arrays and multiple output arrays, but it captures the essential features just to think of one input and one output. But there are 5 key features about this, the type of our problem in particular that motivate this work. So the first is that our input and or our output arrays are too big to fit comfortably in main memory, so we need some way of dealing with that. The second feature is that there is some part of the computation that we want to do that can be parallelized. So that may be some of the initial steps of the computation that could be parallelized, or some of the final steps of the computation that could be parallelized, but they could be parallelized by breaking our input and or our output tensors up into chunks. And so we want to be able to make some use of that. And we may not be able to parallelize the whole thing. There may be some part in the middle of our computation where we do have to bring everything together, but definitely some parts of it could be parallelized by working in chunks. And actually, we have quite a lot of problems that just look like this, that are embarrassingly parallel. So we can just compute something on each chunk completely independently and store that in the output. A third feature is that I/O is the bottleneck. So for many of the problems, the computational complexity is not that great, actually. We're not trying to fit any very, very complicated statistical models. We're just trying to do some summaries of the data. So a lot of time is spent in reading and or writing the data. And there are 2 sort of essential reasons why it may be the bottleneck. First is that your I/O bandwidth may be limited, so just the amount of data that you can suck in is limited. But also, if any part of your I/O stack is not parallel, is forcing things to happen in serial, then obviously that's going to, it doesn't matter how many compute nodes you've got, you're still going to be bottlenecks on I/O. A fourth feature is that the data are compressible. This is something that I've sort of, really been exposed to through this work, but compression is an extremely active area of innovation. There's a lot of new work happening in compression. And modern compressors are ridiculously fast with very good compression ratios. So we can really leverage this to trade some of our I/O for compute. And in our case, our data are compressible sometimes by up to 50 times, so it can make a really dramatic impact. And the fifth feature of our problem is that we care about how fast things go. And the reason we care about it is because we're collecting these incredibly rich data sets that could answer many, many questions. I'm sure this is a very common theme for many people here in this room, but basically we're doing exploratory science, which means that we have these many, many rounds of interactive work, summarizing, visualizing, hypothesizing, modeling, testing, and many different iterations. And so the faster that we can work and the more interactively we can work, the better we can explore the data. So we have these five key features, and that's what's driven this work. So the solution, or an obvious way to go to try and solve this problem is we need two pieces to the solution. The first is we need some sort of computing framework that allows us to break our computation down into chunks and to run those chunks of compute in parallel. But also to go with that, we need some sort of storage library that works well with that and that can read and or write our pieces of our data in parallel too. And the basic idea is that if you align the chunks in which you've organized your data in storage and the chunks in which you're doing your computation, if those things are aligned, then you have a very good match and things should work very nicely in parallel. You should get as much parallelization as you can possibly get. So that's the basic idea, that's what we're looking for. At the time when we were trying to work through some of these issues, we became aware of Dask. I think everyone actually, I'm getting the sense that everyone's very familiar with Dask now, but basically this was a very attractive piece of software for us, and the reason why I really wanted to use it was because it allows you to work in this very familiar API. We didn't have to drop tools, throw away our existing code. We can work in a NumPy-like API. And so we can leverage as much of both the existing code and the existing knowledge that we had to be able to scale up our computations. But also it scales both down and up. So actually a lot of the problems that we had, I could run on my laptop actually quite effectively. And I was really keen to then, but my laptop's got 4 cores, each has got 2 threads. So I can do a lot in parallel on my laptop. So I really wanted to max out the computation on my laptop. One of the most frustrating things I've ever had is running something, watching your CPU status bar and just seeing a little thin blue line with only one of your cores running at any one time. That started to really, really bug me. So I really wanted to max out my system monitor. But also, although I was particularly focused at that time on working locally, the fact that I knew that with just a bit of configuration swap out, you can run exactly the same code on a large cluster, giving that opportunity for scaling up and out really attracted us too. So we really wanted to use Dask. And also a related thing that happened is that while I was working through some of these issues, the Pangeo project was working to address some similar issues in the geosciences, where they have extremely large data sets, and they'd like to be able to handle them both on HPC and cloud platforms. They also wanted to use Dask. They also needed some sort of appropriate storage solution that would work well and play well with Dask. And they were particularly interested in leveraging cloud object stores to get really large scale computations done. So things like Amazon S3, Azure Blob Storage, Google Cloud Storage. So this distributed storage requirement. So we have at least one nice parallel computing package in Dask. What options do we have in terms of storing the data? So I'll just mention that the two packages that I was looking at and working with at the beginning of this work, the first is obviously HDF5 and H5Py. So I'm sure most people are familiar with this library, but it allows you to store multi-dimensional arrays. You can divide those arrays into regular shaped chunks. Those chunks can be compressed. You can also group your arrays into a hierarchy, which is very convenient if you've got lots and lots of arrays. And with H5Py, you get this very smooth integration with NumPy. You can just pull slices of your data directly out of off disk and into memory. So this was really nice. And actually, the first thing we did was migrate from our legacy text-based formats to HDF5. And that really was a quantum leap for us, actually. It really sort of opened my eyes as to how fast you can get things to run if you have efficient binary I/O. So this was a really big leap for us, actually, to start using HDF5. But as we started to scale up, you start to hit some of the limitations that exist with HDF5. So some of these are, there's no There's no support for thread-based parallelism. You cannot do parallel writes with compressions. If you're compressing your data, you cannot write in parallel different chunks of your data. It's not very easy to plug in a new compressor, and there were some compressors that I wanted to play with, but I'm not a C coder, so it was not straightforward for me to do. And at the time, there was no support for using HDF5 in the cloud, although more recently there is this new work from the HDF group called Kita, so that's definitely worth checking out. And the other package that I was working with is this package called bcols, which was developed by Francesco Ted, who was the main developer behind PyTables. And bcols was a sort of lightweight alternative to PyTables. And it's primarily intended for storing table data, so columnar storage. But it did have this class which allowed you to store multi-dimensional arrays also. And the thing that was very attractive about it was that actually, when you looked at the underlying code, it was simple in a good way. So when I actually looked at the underlying code, I could get some sense of how it worked and got some sense of the fact that actually it's not that complicated. It's not that difficult to think about how to do chunk storage. Also, one thing that bcols did is that they had a very simple way of storing the data on disk. So rather than just using one file, as HDF5 does, and you store all of your chunks, all of your metadata in one file, bcols just exploded that out, and so you had separate files. So for a single array, you would have a metadata file, and then you would have separate files for each chunk. And so that made me think, well, actually, maybe we can simplify this, and if you've got separate files for each chunk, that frees you up a little bit in terms of if you want to then write your chunks in parallel, you don't have any complicated work to do to figure out how to allocate space in a single file. You can just write all your files in parallel. So that was very attractive. But bcols wasn't really trying to solve the problems that we were trying to solve. There was only chunking in one dimension. If you've got multi-dimensional arrays, you often do want to chunk in multiple dimensions. And there was no support for different storage backends. So I asked the question, the fateful question, which perhaps one should never ask, but how hard could it be? And I have to say, actually, looking at the bcols code really sort of made this less of a crazy question. How hard could it be to implement a chunked storage library for multi-dimensional array data that supports parallel reads, parallel writes, was easy to plug in new compressors, and also easy to plug in different storage backends like Cloud Object Store? So that's what we're trying to do. So if this talk was a movie, this would be the point at which there would be a montage sequence. There'd be some very emotive music, lots of furious typing on keyboards, joy, elation, despair, frustration, babies being born, kids growing up, all of those things. But I'm just going to ask you to imagine that, and I'm going to skip forward a few years to talk about where we are now. And so now there is a Zarr Python package. You can install it with pip or conda. The current version of the package is 2.3.2. And Zarr is heavily inspired and follows the conceptual model of HDF5. So you can store multiple arrays and organize them into a hierarchy of groups. Each array is divided into regular shaped chunks, just like in HDF5, and each chunk is compressed before storage. So that's the basic model that we're working with. That's the same. And so here's some code just showing you how you do some things with Zarr. So the first thing that you would do normally is you would decide on what your storage is going to be. So here I'm setting up a store, and this is a directory store, which means I'm going to store my data as files on the local file system. So example.zarr will be a directory in my local file system. Once you've set up your store, you'll then set up your hierarchy, the root of your hierarchy. So I'm just going to create a group using this store. So root is going to be the root of my hierarchy. And then if you want to create arrays within that group, you can use some NumPy-like array creation routine. So you can use this zeros method, for example. You give it a name, so this is the name of the array. You give it a shape, just like you would for a NumPy array. You give it a dtype, just like you would for a NumPy array. You have to specify the chunks, so you have to specify how this array is going to be broken up. So here we're creating an array that is 10,000 rows, 10,000 columns, and that's broken up into chunks where each chunk is 1,000 rows and 1,000 columns. So that means there's going to be 100 chunks here in total, and those chunks are going to be arranged in a 10 by 10 chunk grid. I hope that all makes sense. If you are migrating from HDF5 or H5Py, then there's also an H5Py style API, so you can use this create dataset method, which does basically the same thing, creates an array. You can create very big arrays if you want to. So here I'm creating an array which is 100 million rows and 100 million columns, divided into chunks of 10,000 by 10,000. That's a very, very cheap operation, so you can just do that on your laptop. It will return straight away. If you want to get a bit of diagnostics on an array, there's this info property. So here I'm getting some diagnostics on that big array that I created. So here's the shape, the chunk shape. This is the compressor. That's the default compressor. This is the store type. So if you loaded this entire array into memory, it would be a 35 petabyte array. But in fact, only 355 bytes are stored on disk at the minute, and that's because all we've stored is the metadata for the array. We haven't stored any data. So the chunks that you actually need to store data are only initialized when you write to them. If you haven't written to them, there's not going to be any data stored on disk. If you want to write into an array, you can use the same API that you would use for writing data into a NumPy array or an H5Py dataset. So here I'm just writing some data into the first row and the first column. And if you want to read data out, again, you use the same API that you would for slicing a NumPy array or reading data out of an H5Py dataset. So here I'm just slicing out the first 1,000 rows and 1,000 columns from that array. And just to illustrate that chunks are initialized on write, so when I did that write, I wrote into the first row and column. That write spanned 3 separate chunks. So now I have 3 chunks that are initialized in this array, and I've got 4.9 megabytes of data stored for this array. And just to then show you under the hood what's happening, what Zarr storing on disk. So if I just use my operating system tree function and show the directory structure, there's this example.zarr directory. Inside that, there's this directory named big. That corresponds to the big array that we created. This file, .zarray, that's the metadata file. And these 3 files here are chunk data files. So there's 1 file for each of the chunks that we created. And then just to show you what the metadata looks like, so this is the metadata for that array. It's a JSON file. Here's the shape. Here's the D type. Here's the chunks. Here's the configuration for the compressor. So fairly hackable. And then just to say, you can read data out from regions of the array that you haven't written to yet. So here I'm reading out data from the last 1,000 by 1,000 square of that array. And that hasn't been written to, but you can read it. It will just get filled in by the fill value for that array. So it's as if it's filled with that value, but there's no data actually being stored. And you can try and read the whole array if you want, but obviously I can't read this particular array. Okay, so I'd like to spend a little bit of time now talking about how you can plug in and use different storage backends for Zarr. So I've talked a bit and illustrated how you use the directory store backend, but there's a number of alternatives for local file system storage. There's a zip store. There's stores for using different key value databases. So there's the DBM store, which you can use with Berkeley DB, for example, LMDB store, SQLite you can use. There's stores for some network databases like Mongo and Redis. And there's also store classes that you can use for Google Cloud Storage. So Azure is supported by a store class that's within the Zarr codebase. If you'd like to use S3 or Google Cloud Storage, there are store classes which are provided by these third-party packages, S3FS and GCSFS, which are part of the Dask project. And just to illustrate these differences, so here again I'm using the directory store and just reading some data, accessing the data the array that I created earlier. If you want to do something a bit, and just to remind you again, so here's the actual underlying files that were on disk that we created for that array. If you want, you could zip up those files. So if I zipped up all those files, just created a single zip archive, you could then use the zip store class and you could read data directly out of that zip file. So if you need to move your data around or you want some archival storage that doesn't have lots and lots of separate files, this can be quite convenient. Alternatively, you could copy all of those files up into cloud storage. So you could use gsutil, for example, to copy each file up into object storage. And then you could set up your store using GCSFS, using this GCS map class. So here, Zarr demo is the name of the bucket, and example.zarr is the path within that bucket, and then everything below that is exactly the same code. And just to show you, again, what's happening under the hood, so this is just a screenshot from the Google Cloud Console. Here's my Zarr demo bucket. Here's the example.zarr path. There's a subpath big for the array that I created. And what were files on my local file system have now become objects in object storage. So we've got an object for the metadata and then one object for each chunk. And so just to unpack that a little bit and explain what's going on and how the storage API works. So here I'm just giving an example of a much smaller array. So this is a 10 row by 6 column array, and I've divided it up into 5 chunks which are shaped 5 by 3 size chunks. So here are my 4 chunks of this array. And the way that we store these data using Zarr is that each chunk is given a key, and the key is formed from the coordinates of the chunk within the grid. So this top left chunk has a key 0.0, and this chunk, which is next along in the grid, has a key 0.1. So when you're storing those data, you take the contiguous binary data for that chunk. You then pass it through optionally some filters and a compressor. That gives you a sequence of bytes. And then that sequence of bytes just gets stored in the store as a mapping from the key to the sequence of bytes. So conceptually, all the store is a key value store where keys are strings and values are sequences of bytes. So that means that any system that can expose a key value type interface can be used as a Zarr store. And in Python, we use the mutable mapping interface to represent this interface. So basically, if you have a class which implements getItem, setItem, getItem to get a value for a key, setItem to set a key value pair, and then iter to iterate over the keys, that can be used as a store. So anything that is like a dict can be used as a store with Zarr. And just to illustrate that, so here is the implementation of the zip store class. I've cut a couple of bits out of this just to make it fit all on one slide, but this is basically the essence of it. Here I'm just wrapping some of the underlying zip file module calls to allow a zip file to behave like a key value store. So the implementation of a store is usually relatively straightforward. Okay, so now, how does Zarr support parallel computing? What can you do? What can't you do? So if you have a Zarr array, it can support multiple concurrent readers. So you can launch as many concurrent reader processes as you like. They can all read in parallel. You can also have a Zarr being written to in parallel by multiple concurrent writers. And you can do multi-threaded parallelism, or you can do multi-process parallelism. And we release the GIL during the critical sections, which are usually compression and decompression. So even if you're using multi-thread parallelism, you usually get good parallelism. I've added this little asterisk in here because this does depend on which store you're using. So not all stores will support this type of parallelism. For example, you can't do parallel writes into a zip file, but you can do parallel writes into a directory store, and you can do parallel writes into object storage. And so now, you can use something like Dask together with Zarr to get both parallel computing and parallel storage. So, for example, you can set up some store, whatever that store is. You can access your input data, your array. Let's use this big array that we created earlier. You can then use the Dask from array function to wrap that as a Dask array. So that will set up an input array where the chunks of the input computation are aligned with the chunks of the storage. You can then set up whatever computation you want to do. If the output of your computation is relatively small, you can just call .compute, which will compute the result and load it into a NumPy array. But if your compute is large, you can then use the toZarr function from Dask, and that will then handle parallel storage of the different output chunks into your output array. So the trick the trick here is that, so I'm just going to talk a little bit more about writing and parallel writing. So what we're expecting here is that when you're writing in parallel, all of your writers are writing to separate regions of your output array. So your writers are never trying to write into the same element of your output array. But there is a question that arises, and the question is, do you ever need write locks? Do you ever need to manage any synchronization between your writer processes? And so that depends on how your writer processes are aligned with your chunk boundaries. So if your writers are writing to separate regions of your array, and those regions are aligned with the boundaries of your chunks, then your writers are never ever going to contend for a chunk. So you don't need any kind of locking. You can just write in parallel. But it can happen that if your writers, although they're writing separate regions of your array, if those writes are not aligned with your chunk boundaries, then it can happen that two writers can end up in contention for the same chunk. So if you're going to do this, then you do need some sort of locking to make sure that you don't end up in contention or lose data by two writes happening at the same time. And Zarr does have support for chunk-level write locks, so you can do this if you really want to. But pretty much what everybody does is they just set up their computation so the writers are writing and their writes are aligned to chunk boundaries, and then you don't have to worry about locking. Because locking's hard to do, especially in a distributed context. So it's best to avoid if you can. But there is more information on synchronization if you want it in the tutorial. So I'm just going to then add a little bit of information briefly about support for different compressors. And just to say again, compressors can just make a ridiculous difference. So modern compressors are incredibly fast. So this is just some benchmarking I did on some genomic data that I work with. In this plot, I'm just benchmarking different compressors, their write speed, their read speed, and their compression ratios. So the x-axis is the compression speed, the y-axis is the decompression speed, and the size of the blob is the compression ratio that they achieve. These three red blobs down in the bottom left, those are the three compressors that are available in the Python standard library, so zlib, bz2, and LZMA. But the others are different combinations of a meta compressor called BLOSK with different internal compressors and shuffle filters. So one option that I like very much is this option here. This is BLOSK with Z standard and the bit shuffle filter. That gives me a 50 times compression ratio, which is very competitive with these other standard library compressors, but I get just many, many, many times more compressed speed. And if you're willing to sacrifice a little bit of compression ratio, then you can get ridiculous, 10 gigabyte a second compression speeds. So this can really, really speed things up and deal with any remaining bottlenecks you have in your I/O systems. So actually, all of the compressors that are available in Zarr have been factored out into a separate package. So we actually have a separate package called num codecs that provisions a bunch of different compressors that you can use with Zarr. So there's support for BLOSK, Z standard, LZ4, as well as the stuff that's in the standard library. And the way you use that is you import some compressor from num codecs, and then you just instantiate it as a compressor. So here I'm using BLOSK, but I'm using Z standard as the internal compressor, and I'm using this bit shuffle filter. And then you just pass that in when you're creating your array. So that allows you to configure your compressor. And if you want to write a new compressor, you have to implement this codec interface. That means that you basically need to implement two methods, encode and decode. And they use the Python buffer protocol. So it's expecting to receive and then return anything that supports the Python buffer protocol. And again, just to show you that that's relatively straightforward, so this actually is the implementation of the zlib codec in num codecs. So you have an encode and a decode method, and those are just wrapping calls to the zlib module from the standard library. So it is relatively straightforward to implement and then plug in your own compressor. So one thing that we've tried to do here, as well as implement a Python package, is describe the protocol, describe the format, describe what we're doing here, so that others might be able to implement the same protocol in different programming languages. So we wrote a specification, storage spec. So the current Python package implements the version 2 of the storage spec. And we do have some other implementations. So Z5 is a C++ implementation that uses X Tensor under the hood to deal with arrays. Just published this week is Zarr.jl, which is a native Julia implementation for Zarr. There's also a Scalar implementation, and Unidata recently announced that they're working on support for Zarr with cloud object storage in the netcdfc library. So these are at different levels of maturity, and there's different levels of feature completeness. We're definitely not all at parity, but there is work ongoing in other projects. So I have 1 minute left to tell you about some of the other cool stuff that's going to be done with Zarr. So we'll see what we can get done. Hopefully this will come up in other talks as well. But Xarray and Intake both have integrations with Zarr, which has been work that's been driven by the Pangeo project. And Pangeo use both Intake and Zarr for their cloud data store, which contains many open data sets from the geosciences. And Intake's a really nice project which allows you to manage your data catalog, so that a lot of the boilerplate about setting these things up is very easy. So that's a really nice solution which I want to copy for genomics. The Met Office Informatics Lab have been doing some really cool stuff about how to deal with their weather model data, which they're generating at the rate of hundreds of terabytes a day. So they have some particularly unique challenges, and they're pushing Zarr in some interesting directions. Microscopy is another very interesting area, and I will just point you to OME's blog post about this. And I don't have time to say more, I'm sorry, but Shannon Axelrod gave a really nice talk this morning about single-cell biology. There's a number of different groups who are exploring the use of Zarr in the context of that, and that's another very rapidly growing area, so it's very exciting. Okay, what's in future? So actually, independently, another group was inventing a very similar solution to Zarr. That's called N5. We are now working together to bring those two approaches together and bring them together in a single spec. So we're working on a new version of the core spec. But the current package is mature. It's used in production, so it's ready to go. So please don't wait for that to be done before you start using Zarr. Definitely the best part about this has just been meeting lots of people and interacting with lots of people and learning about other areas of science. So I hope that can continue. And thanks very much for listening.